Hello learners, welcome to the second part of the presentation on lubricants under the topic of applied chemistry. In the first presentation, we had discussed about the lubrication, its types and viscosity. Now we will discuss further. The another property of lubricants is cloud point. It is another index of dissolved wax concentration which may be defined as the temperature at which the cloudiness appears in the sample of oil under standard conditions because of wax separation. Lubricants also undergo oxidation, hydrolysis and pyrolysis. The property of lubricants to undergo degradation is different for different lubricants and mainly depends upon the composition and the purity of the lubricant. As a result of oxidation, the lubricant undergoes decomposition and its lubricating property is also affected. Hence, certain antioxidants are employed in the lubricants to avoid oxidation. Another property is flash point. It is the lowest temperature at which the lubricant oil gives off enough vapors that ignite for a moment when a small flame is brought in contact with it. That is, the vapors form inflammable mixture with air and catch fire when flame is applied. It is very important to test the flash point of the oil to be used as lubricant. It is not advisable to use an oil as lubricant which flashes or reaches combustion temperature under conditions of lubrication. This is due to the fact that spontaneous combustion of oil vapors occurs if the oxidation is so rapid that heat of oxidation is not dissipated so quickly as to avoid the reaching of flash point or combustion temperature. When lubricants such as esters are exposed to moisture at high temperatures and in the presence of acids and alkalis, they undergo decomposition as a result of hydrolysis. Polyethers and halides are hydrolyzed only under drastic conditions of hydrolysis, and polysiloxanes are hydrolyzed easily by alkaline solution. It is therefore necessary to use those lubricants which are not capable of hydrolyzing under lubricating conditions. Samples having lower Koch numbers are recommended as better lubricants. When organic lubricating oils are exposed temperatures greater than 300 degrees centigrade, they generally undergo cracking, which is a free radical mechanism. The rate of cracking is different for different lubricants and is generally enhanced by oxidation. Hence, lubricants used should also not crack under lubricating conditions. A good lubricant is that which does not form emulsion under lubricating conditions, and if it forms an emulsion, the emulsion should break off immediately or very quickly. There are some lubricating oils which are capable of mixing with water to form an emulsion, that is emulsification, and the emulsion has the tendency to deposit dirt, grit particles and other foreign matter. When lubricant containing these solid particles is used in lubricating system, it may cause abrasion and may even damage the sensitive part of the machinery. There are certain additives which are mixed with lubricants to check the emulsification tendency of the lubricant. Another property is oiliness. Capacity of a lubricant to stick on the surface under pressure or load is called oiliness. Vegetable oils have oiliness, but mineral oils have much less or no oiliness. Additives like vegetable oils and fatty acids are added to mineral oils and improve their oiliness. Now we do the classification of lubrication. Three types of lubrications are there: complete fluid lubrication, boundary lubrication and extreme pressure lubrication. Starting with complete fluid lubrication. Here, one of the rubbing surfaces is slightly displaced in relation to other and a wedge-shaped film of the lubricant is formed between the two surfaces rubbing against each other. The pressure developed in the wedge-shaped film supports the load and prevents the direct contact between the rubbing surfaces. The lubricant film covers or fills the irregularities of the sliding or moving surfaces, and the lubricant forms a thick layer in between them. As a result, there is no direct contact between the material surfaces and wear is considerably reduced. The resistance to the movement of moving or sliding part is only because of the internal resistance between the particles of the lubricant moving over each other. The friction between the two lubricated surfaces depends upon the dimension of the film and of course viscosity of the lubricant. In fluid film lubrication, for example, the lubricant must have minimum viscosity under working conditions, and at the same time it is expected to remain in place and separate the surfaces. In such a system, friction does not depend upon the load but depends upon the viscosity, thickness of the lubricant and relative velocity as well as the area of the moving or sliding surfaces. The coefficient of friction in such cases is extremely low, being of the order of 0.001 to 0.03. In the case of shaft running at a fair speed, hydrodynamic friction occurs and a film of lubricating oil covers the irregularities of the shaft and that of the bearing surfaces. Moreover, there is no direct contact of metal surfaces with each other. As a result, the resistance to movement is caused due to the internal resistance of the lubricant. It should be noted that in fluid lubrication, there is no friction between the surfaces and the wear is almost negligible. So, in the fluid lubrication, wear decreases as the friction decreases. In boundary lubrication, decrease in friction does not decrease the wear to the same extent as the decrease in friction, so minimum friction is not achieved by minimum wear. Complete fluid lubrication is provided in delicate instruments such as watches, clocks, guns and light machines such as sewing machines, scientific instruments, etc. The most satisfactory and widely used lubricant for this type of lubrication are hydrocarbon oils, which are blended with selected long chain polymers in order to maintain suitable viscosity of the oil in summer, winter and other seasons of the year. Some antioxidants such as aminophenols are also added to the hydrocarbon petroleum fractions because these usually contain minute amount of unsaturated hydrocarbons which are susceptible to oxidation under operating conditions. Now moving on to the next type, that is the boundary lubrication. It may take place under the conditions when the relative speed of the lubricated surfaces is insufficient to develop pressure in the lubricating film to carry the load. Such condition may develop when a heavily loaded bearing is suddenly stopped or started. Boundary lubrication is used when the load on bearing becomes greater than the pressure developed in the lubricating film or when the surfaces are not perfect and the load is carried on high spots. Boundary lubrication is suitable when a continuous film of lubricant cannot persist and direct metal to metal contact is possible because of various reasons. For example, when a shaft starts moving from rest or speed very low and load is very high or viscosity is extremely low. Under all these circumstances, friction between the lubricated surfaces lies on absorbed boundary layers of the lubricant. The load is carried by the layers of the absorbed lubricant on both the surfaces. The coefficient of friction in such a case is generally 0.05 to 0.15. This friction is dependent mainly upon the nature of material of surfaces and also on some characteristics that can be determined by the chemical properties of the lubricant. The effectiveness of boundary lubrication primarily depends upon the structure and chemical properties of the oil to be used for boundary lubrication. The lubricant used in such type of lubrication should have long hydrocarbon chains, polar groups to enhance spreading and orientation over the metallic surf at high pressure, lateral attraction between the chains, and active atoms or groups capable of forming linkages with the metal or other surfaces. Other important properties of boundary lubricants are low pour point, high resistance to oxidation and heat, and high viscosity index. Lubrication by boundary lubrication does not depend upon the viscosity and resistance to shearing of the lubricant, because lubricant layer in this type of lubrication is in immediate contact with the metal surface. However, these properties have been found to affect the lubrication because true boundary lubrication conditions are also difficult to achieve. These properties of lubricant determine the formation of a wedge of the lubricant between the surfaces in case of fluid lubrication. The third one is the extreme pressure lubrication. When there is high load and high temperature generation between the sliding surfaces, extreme pressure lubricants are used. This type of lubricants contain organic compounds containing sulfur, phosphorus, lead, chlorine, etc. as extreme pressure additives. Sulfur and chlorine present in these additives react with metal to form sulfides and chlorides when both sulfur and chlorides are present. These metallic chlorides, sulfides or phosphides have high melting points and act as good lubricants under extreme pressure and extreme temperatures. The organic compounds decompose and form high melting lubricating films on the metal surfaces. These additives form a more durable film on the metal surfaces, and thus film is capable of withstanding high loads and high temperatures. As discussed before, these additives are the organic compounds having active radicals or groups such as chlorine as in chlorinated esters, sulfur in sulfurized oils, and phosphorus as in tricrysyl phosphate. Some examples of extreme pressure additives are compounds containing oxygen like fatty acids, ketones, esters, etc., containing sulfur or sulfur and oxygen, chlorinated wax, sulfurized fats, sulfurized olefins, organic compounds containing lead and both chlorine. Now, synthetic lubricants. Mineral lubricants, even with additives, cannot be used under various abnormal conditions. For example, when the temperature is extremely high or the atmosphere is chemically reactive. Under such conditions, synthetic lubricants having appropriate properties to be used under abnormal conditions are generally employed. Such synthetic lubricants are prepared by hydrocarbons, polyglycols, esters, polycarbonates, amines, silicones, and fluorine derivatives, etc. In fact, synthetic lubricants are developed to meet the most severe and drastic operation conditions, such as those existing in aircraft engines, in which oil may have to be pumped at minus 50 degree centigrade. During takeoff or landing, the same oil may be heated to as high a temperature as 250 degree centigrade. Hence, it is necessary for the oil to maintain satisfactory properties. The oil to be used at high temperatures and high operating pressure is expected to have high resistance to oxidation and high viscosity, and at the same time it must also possess sufficiently low freezing point, and it should also be non-inflammable. Modern synthetic lubricants have been prepared by taking all these factors into consideration and have a number of distinguishing characteristic features. They are inflammable and have high flash points, high viscosity index, high thermal stability at higher temperatures. They are, however, very costly, so they are used only when they are badly needed. For most common purposes, blended petroleum oils are good and synthetic lubricants are needed only in special circumstances, for example, in certain specialized military and industrial uses. Let us talk about some synthetic lubricant examples. Polymerized hydrocarbons such as polymerized ethylene, propylene, butylene, etc., having molecular weights ranging from 250 to 50,000 are used as synthetic lubricants. Although these hydrocarbons have chemical and physical properties similar to the lubricants obtained from petroleum fractions, but they have some distinct advantages over the equivalent petroleum products. For example, these synthetic lubricants can be used at high temperatures as residue-free high temperature lubricants. They are light in color and free from non-hydrocarbons, and they have better electrical properties. Polyglycols and related compounds such as polyethylene glycol, polypropylene glycol, their ether and esters, higher polyalkylene oxides, polythioglycols, and polyglycerol ethers can be used as water-soluble and water-insoluble lubricants. Water-diluted lubricants, for example, can be prepared by polyethylene glycol or polypropylene glycol to be used in rubber bearings and joints. After applying to metal surfaces, they can be easily removed by water flushing. Higher polyalkylene oxides and polyglycerol ethers absorb a considerable amount of water, and although they are not soluble in water, and temperature has no effect on their viscosity. Polyalkylene oxides undergo decomposition into the volatile parts under high temperature, and their volatile parts undergo oxidation. Hence, these lubricants are very useful at high temperatures and used in rolling bearings of sheet glass machinery. Fluorocarbons and other compounds, for example, tertiary amines, ethers, esters, which can be completely fluorinated, are also used as synthetic lubricants. They are chemically inert and resistant to all chemicals except molten sodium. They are not decomposed easily by heat. They are also not easily oxidizable. Natural fats and oils are esters of glycerides. They have higher freezing points and they can be easily oxidized. That is why they cannot be used as lubricants, whereas diesters of glycol and aliphatic dibasic acids, as well as those of aromatic dibasic acids and triesters of phosphoric acids, etc., have been found to be good synthetic lubricants. It is because of that their viscosity is not much affected by increase in temperature, their volatility is very low, they can be readily oxidized, but this property can be reduced by adding additives. Moreover, they also act as good lubricants even at low temperatures. Esters as lubricants can, however, be decomposed by steam and acids as well as by alkalis. Organic amines, imines and even amides are good synthetic lubricants having high viscosity index and low pour point. Silicones and the products obtained by hydrolysis and decomposition of chlorosilicones are also employed as synthetic lubricants. It's because they have low viscosity temperature coefficient and are not readily oxidized up to about 200 degrees centigrade. They are, however, oxidized quickly above 200 degrees centigrade and undergo cracking at about 225 degrees centigrades. Silicones are very useful for low temperature lubrication of small parts. Now we have discussed synthetic lubricants and the examples of synthetic lubricants also, but selection of lubricants is also very important. A careful study of various properties and their correct interpretation is extremely important because properties of a properly selected lubricant should remain same and do not change under service conditions, otherwise there may be a lot of problems. And that is why at the start of the lecture when I said that lubricants form an important part of chemistry in daily life, we have to be very selective about the choice of lubricants which we are using for our machinery or for some other system. So learners, in the two lectures on lubricants, we have talked in detail about the lubricants, their functions and the types of lubricants, for example, the liquid lubricant, the semi-solid lubricants, the solid lubricants. We have also studied in detail about the properties like viscosity, viscosity index, cloud point, pour point, flash point, oiliness of the lubricant. We have also discussed the three types of lubrications and synthetic lubricants in detail. I hope this is going to be a very useful topic in your daily life as well. Thank you.